presentation? Can you see anything else on it?
I can see your little mouse whizzing around, and
okay,
I can
that's
see the
fine.
presentation.
But there's no other sort of rude pictures or anything else on the screen then?
No.
That's good. Right.
Unless
okay.
you meant to put them there, of course.
Right. Okay. Well, let's get started then. So what I'd like to do first of all is to remind you of how we calculate overthrow on circular curves. And I'll take you back to the British Railway Track edition, 6th edition, published by the PWI, where we actually went into some detail at that point to say this is how you calculate curve overthrows. Remember that this book that we have rather predated any of the computerized calculations that we currently use. So there's very simple calculations brought in, which effectively said that you can calculate the overthrow at the center of a vehicle by one formula, the overthrow at the end of a vehicle by another formula. And there are two formulas as well for looking at intermediate overthrows along the vehicle, depending on whether you're inside the bogey centers or outside the bogey centers. Now, they're very simple formula. They're quite approximate. There's errors associated with them because they don't take into account some of the finer points of overthrows, such as, for example, obliqueness on curves. But nevertheless, we've used those for years to say if we've got a curve of X meters radius and we've got a vehicle that's got bogey centers of say 14 meters, then we can calculate how much overthrow would be applied at the center, at the end, and at any cross section. Now, that's fine for circular curves, but when transition curves, of course, you can't actually define what the radius is that the vehicle is on. So there was a method that was developed by the Southern Railway Company, Southern Region as it later became, where effectively we looked at ADI along the track and used that as an indicator of what was going to happen as the vehicle went down the transition. Now, this process was introduced into a number of clearance softwares back in the day, particularly interactive track design, which, as you can remember, Nick, and effectively this methodology is embedded in, for example, the standard files that are produced by equipment manufacturers. And there's a value in the files called R plus J and R minus J. Now, J is just the alphabetical number for 10. So if you go A, B, C, D, F, G, H, I, J, J is actually 10. And that means that we're looking at the radius ahead of a point. And on this particular diagram you've got in front of you, the point we're considering is the where the rubber is sitting on the side of my trying Hornby track layout, which I find exceedingly useful to demonstrate what's happening in overthrow situations. And in this particular case, what we can see is that the overthrow at the point of the structure, we call it R. There's the radius at the point of the structure, the curve radius. There's a curve radius behind the structure, which in this particular case, the center of the vehicle is sitting on. And there's a radius ahead of the structure, 10 meters, which the vehicle will be sitting on when the center gets to that point. Now, what we use is a simple formula that says we consider the radius that the end of the vehicle is going to see as being the tightest of the radius 10 meters ahead or the radius 10 meters behind. Now, that's a really bold simplification, but nevertheless, in the days when this methodology was implemented, it enabled you to calculate, for example, the transition throws going into places of tight curvature change, such as the throat stations. And in particular, this method was used to regulate the overthrows and the track position in the throat of Waterloo Station, which is one of those places that had a reputation for brass door handles on the side of the on the ground, because trains would pass each other, and the old C1 rolling stock, the door handles would knock themselves off. Originally called frangible items, not something that we go for these days. But that was where that methodology came into play. What I'd like to do is to show you the practicalities of this, because I took a series of measurements from Waterloo Station, platform 2. And what you can see here is the versine going into the station on platform 2. And we can see that it's not really terribly smooth. The measurements show a variation in the versine that ultimately leads into what we can roughly calculate as being a reverse curve that goes through the throat and into the platform. Now, one of the problems, if you start to look at this graph, you can see that if you're looking at the radius 10 meters ahead of a point and the radius 10 meters behind a point, it's rather dominated by the roughness of the measurements. So if you wanted to take the tightest measurement, then actually there is some element of, shall we say, choosing what that radius would be. But in strict terms, if you choose radius plus or minus 10 meters, you end up with a certain amount of randomness going into it. And the net result of that is an inaccuracy in the calculation. And I should say the points on this graph are at 5-meter spacing. So one of the things that's being thought about at the moment is where we have measured data, and I'm talking about measured data because the methodology defined by the southern region was actually based upon Hallard data. What we can look at in terms of measured data is actually to put a smoothing in. And I think if you can look here, you can see an orange line that's been put in here, a yellow line, which is the smooth version of that curve. And what that allows us to do is actually to define the sections of the track, for example, that are straight, and the sections where the curvature changes by filtering out the roughness. And filtering out the roughness is a very delicate art. When you're looking at this, as those of you who've done Hallard in the past will remember, you have to look at it from the point of view of using common sense and saying, where does my curve start and finish? And choosing a filter that you put on the track, it's very important to make filtering to get a smooth geometry out of it. You don't actually take out the information that you need, which in this case is the transition data. So the net result is if we take our rough profile and filter it, we end up with a smooth profile that actually is far more indicative of the curvature in the track than taking two measurements, one 10 meters and one 10 meters behind. So taking that forward, what we can do is we can look at the requirements for our filter to say that we have to remove the roughness of the measurement, that we need to preserve the transition, and we have to consider what the error tolerance is. In other words, we can't use a filter to get rid of badly measured data, but what we can do is use a filter to take data that has the normal measuring accuracy roughness in it and the track roughness that we measure and produce a decent smooth profile, very similar to what we get in terms of Hallarding or putting a smooth Hallard profile across a series of measurements that we've taken. And the options we've got at our disposal are a number of things. The first thing is the filter base length. That's saying how long ahead and behind is our filter looking to say what data have I got. It's looking at the filter type. There's all sorts of filters that you can use. If you look in Wikipedia, for example, you can find anything from boxcar filters, Butterworth filters, triangular filters, averaging filters. Each one has slightly different characteristics in terms of what it does. We have to look at the filter symmetry. And a classic case of an asymmetric filter will be what a tamping machine sees as it's going through a curve and smoothing it, because the front of the tamping machine is sitting on rough track and the back of the machine is sitting on smooth track. That's providing an asymmetric filter. And the final thing we need to consider is the phase shift of a filter. In other words, something that we're familiar with when we're doing track design, and that is if you're smoothing design, it's making sure that we don't move the transition points and making sure we move the reverse points. So those options are the sort of things we have to look at in terms of filtering our profile. And here we have a almost of what would happen if we had a vehicle sitting on our transition curve. Now it's to scale longitudinally, so that black thing in the middle is to the longitudinal scale, but it's not obviously to scale laterally. It's a very much amplified scale, but we can see now an order of magnitude by order of magnitude how that vehicle is going to behave as it's going to go around the curve. We can see the effect of that transition curve in terms of how the vehicle will relate to the track underneath and in relation to any objects around it, such as the platform in this particular case that we're trying to calculate the overthrows for. So let's have a look first of all at what are the advantages of using smooth curvature. The first advantage that we've actually got is that we can reduce the under or overestimate of overthrow we might have by actually having roughness included in our calculations. The overthrows that we will get by using a smooth profile will more readily match the curvatures that we'd measure for a vehicle going curve, because the vehicle going around a curve is not as susceptible to the track roughness as measuring techniques pick out. And secondly, we can look at reducing the overestimate in intermediate cross-section that can be avoided by the use of the correct curvature. In other words, that it's not just the end and center, it's also the coordinates, it's also the cross sections along the way, which may have things that stick out of them, like platform steps, vehicle steps, yaw dampers, and anything else that we might have on it. On the next slide, I'm going to revert to demonstrating what happens as a vehicle goes around a reverse curve. And we can see here my Triang Hornby model sitting on a reverse curve. And what I want to show you is what happens as a vehicle goes around a reverse curve. And one of the easiest ways to actually, instead of doing it in CAD or anything like that, is quite simply to look at it from the point of view of the uses in real life against a piece of graph paper. Very old method, but it works pretty well for me. And what here is I've run that vehicle through my reverse curve. We can see that there are two lines traced out. The red line is the what's traced out by the front end of the vehicle, and the blue line is traced out by the rear end of the vehicle. Now, there's a very interesting thing about this graph, and that is that we think of overthrow as a translation of the vehicle's static profile into the overthrow given section, which in general on a circular curve is correct, and that is correct. But in terms of a vertical, a curve, what we actually find, and you can see this in the center of it quite clearly, swept envelope of the vehicle widened and it's not translated. In other words, the methodology that we've been using over all these years to look at the transition overs, which translate the position of the vehicle cross section, is actually incorrect. It isn't a translation, it's a widening. So in other words, we're underestimating the overthrow on one side or the other of a vehicle, which could be important. And it's something that for many, many years, we haven't actually taken any account of. So moving on, what I'd like to talk about is not only the advantage of smooth curvature, but also in terms of the transitions, is we can add to it the correct application of end throws on reverse curves. And by end throws, what I mean is the throws for any section that is between the bogey centers and the end of the vehicle. So the methodology that we're looking at here, and which we hope to implement in terms of the software that's developed that we produce, is actually to look at using the methodology of applying overthrows according to the correct radius for every cross section of the vehicle, not just one radius at the beginning, one radius at the end, and then applying the cross sections according to the overthrow they developed as potential increases in width or semi-width of the vehicle in the right direction. In other words, what we should be doing is doing a far more accurate approximation of curve overthrows on transition curves on mainline railway track. Now, I mention this as mainline railway track because, as ever, when we're talking about curve radii, we are talking about the ability to calculate overthrows from that radius, which is an approximation of what you get if you look at compound curves and very, very complex curves, such as we find on metro systems. There's a process whereby we can use strings, line strings, to calculate overthrows exactly, But in terms of line strings, this is actually quite a complex process to introduce it into run-of-the-mill gauging calculations. And what we're trying to do by this methodology is at least improve the accuracy that we currently get with the R plus J, R minus J method that we refer to, and make it mainstream, allowing people to get more accurate predictions of what's happening to rolling stock as it's going through transition curves and reverse curves. And with that, what I'd like to do is leave my presentation at that point and throw the floor open to anyone who's got any questions. And I think, Nick, you wanted that to be done via the chat, is that correct?
Yeah, if possible, if we can do via the... Oh, I can hear myself talking. If possible, we can do that via the chat, that would be good.
Okay, so I am open to any questions that people might have on the methodology of using smooth curvature calculated correctly for every cross-section of the vehicle and calculating the overthrow as a result of that vehicle moving through transition curves.
Thanks, David. I remember once doing a track relaying job at St Blazey in Cornwall, jointed track and a masonry wall against the platform.
Yes.
And we used the unit that was on St Blazey Depot as the gauging device. I guess you'd have had a more scientific way of doing it, perhaps.
I think we're getting more scientific as time goes on, but I think one of the things we have to remember is that sometimes we get caught up in the complexity. So you mentioned, for example, jointed track. We all know that if you happen to take a versine measurement on jointed track, a lot of the inaccuracy comes from when you get close to the joints. And the curvature of the track is not necessarily dependent upon what you measure a versine when it's going across when you're measuring across a joint. Similarly, if we start to look at what comes off measuring trains, what they're measuring is actually what it's seeing, which is a combination of curve geometry and track roughness. And actually determining what's the difference between track roughness and track geometry is quite difficult, because you can look at it and say, actually, a transition is just a bit of controlled track irregularity. And you know, one of the things about gauging that we've often done in the past is confuse the smooth curvature, the geometry that we've got, which is what we're trying to use to calculate our overthrows, versus what we've measured. And for many years, for example, on the National Gauging Database, we've taken the value of curvature as read as it comes out of measuring systems. And of course, that's introducing inaccuracies. So I can see that we've got a question.
We've got a question from Alistair. That's right. Yes. So
yeah.
If I hand over to Alistair. Alistair, your question, please.
Hi, Nick and David. Thanks very much for the presentation there. I have a quick one on when you were defining your roughness and your smoothness. I thought that was very interesting. So
yes,
you were saying as part of your analysis, you take the roughness out of it in order to gain the sort of the smooth track to undertake analysis. But then you stated that the roughness was giving you maybe an overestimated or a conservative value when you were doing your analysis. Is it possible to add that roughness parameter back into your analysis in order to take account of that sort of for your outputs?
Yes, in fact, the roughness is already taken into account. What we're doing, what we are theoretically doing, is we take the overthrow and the dynamic forces from the smooth geometry. In other words, what we ideally want is we want to know what the design geometry is. We then take what we class as the limit state roughness and add that into it later. So in other words, you don't know that the piece of track that you've got is actually at the maintenance limit, so it could be worse. So the process is actually that we consider the geometry to define what the dynamic forces are and what the overthrow should be, and then we add into it the additional roughness that we get if the track was at worst case roughness. The difficulty that we have at the moment is that by using a compound geometry at the beginning, which is a mixture of roughness and smooth geometry, we're actually taking into account the roughness twice. And in some cases, by taking into account the roughness with the geometry, we're underestimating the overthrows and the forces, and in some cases we're overestimating the overthrows and the forces. So to the purists, what we really should be doing is taking smooth geometry and adding in the absolute roughness at the end. And that's really what we're seeking to do by choosing a filter that will take out the roughness, allow us to have the smooth geometry, and then add the roughness in later, which is what the process is.
Oh, thank you. That's very interesting.
Yeah, a lot of people don't realise that we're actually double counting roughness when we do a lot of these gauging calculations, because the theory has been very well calculated. It's just that along the way that we've lost some be an overestimate of actually what's underneath. In most cases, it's going to give us but there would be situations where if your roughness was consistently in one direction, you could actually be overestimating the clearance. Now, I think I saw a couple of other things pop up on the screen then, but I'm not sure where they went.
Sorry, I can see my signals dropping in and out a little bit.
I can see there's a chat now. I can see that we've got some people in the chat here. So
right, okay. Let's take the.
Okay, so
should we go with Stuart to start with?
Stuart Corrie. Well, hi Stuart. Good to see you again. Stuart and I have known each other for many, many years. Yeah, the answer of working with design data where we fully understand the track position is exactly what we're trying to achieve. And I think one of the issues here, of course, is how do we get track design information into our system? And these processes are quite immature. I think the issue really is that what would be really great is if we understood what the design geometry is. And I think the other side of it is to bear in mind that when we actually do look at design geometry, it's very easy to note that design curvature, for example, doesn't change a great deal. If you look at the design curvature at shall we say Slough Station, it's very much as it was when Brunel laid the track down. Change the curvature very much there, and you're going to be pointing off in the wrong direction. So, mostly our design curvature is there, and once we've got it, that's actually what we should be using. So the answer is yes, we really do think about using that, and that's ultimately what we'd like to do. What we really have to do is to improve the methodologies by which we get design curvature in.
I'm a track designer. We work on track design jobs. I can tell you where all the circle centers are.
Yeah,
I can tell you where the straights are. It's not a problem.
That's perfect. And I assume that when you're doing your design work, Stuart, you'll be using that anyway, won't you?
Not normally as part of the gauging process on Network Rail.
Okay.
Which is kind of what this is somewhat focused at.
Yeah, well, I think that's what one of the things we should be striving to do is to get that in, because that is the actual mathematically correct thing to use. We've already differentiated between roughness and curve geometry, and we do work. It should work on the basis of design data. So somehow or another, I think that's something in the process we need to think about, how we get that design data to be available for people to actually use. Okay. The next question we've got is from Okan. It says, would it be possible to find out the method used to smooth the verse signs? Well, I mean, that's very much down to individual choice. What we've chosen to do in this is we've chosen to use a particular type of mathematical filter, which in our opinion, gives us the best compromise between taking out roughness and not destroying the underlying geometry on the sort of curves that we've got on the National Rail network. If you go back to the Hallard methodology that was used, the smoothing that we've done there was based upon the base length of vehicles, and using half chord lengths, which generally would be 5 or 10 meters, depending on what length of survey chord was used. But of course, in practice, in terms of track geometry, when we start to look at what is track roughness, we're using filter lengths of maybe 35 or 70 meters to actually define how rough track is, which is great, but in actual fact, that's more appropriate with saying, how is my track deteriorating, not whether my track is a transition or whether it's a circular curve or whether it's straight track. So I think when it comes down to it, it's horses for courses, and you would be using the methodology to filter smooth versines according to what you're trying to do with it. And you know, a lot of people will be using methods for putting versines, calculate them in. I don't know how common the Hallard method is these days, but that's fairly well defined in what you've got. Next one I've got here is from Giles Haley at Siemens. It says, what do you perceive to be the location and magnitude of the benefit of this method? Is it about marginal gains, and does the available infrastructure support the improvement? That's an interesting question, of course, because in so many of these things, you have to look and say, is the juice worth the squeeze? And I think the issue here is that if we start to look at the magnitude of overestimates and underestimates, the big issues tend to be about using curvatures, say 10 meters away from a point just because it's outside of the bogey centers of a vehicle. And I think we could probably say that on some of our stations, where we've got fairly tight curvatures and particularly tight transitions and reverse curves, I'd say we'd be looking at maybe taking out 10 millimeters or more of overestimate of clearance. And of course, when we start to look at passenger mobility and things like that, getting a platform to be demonstrated as compliant or not compliant is a big problem these days. And there's a lot of places where that sort of magnitude can make a difference. Thomas Corneli, what are the points of differentiating between that would separate this from UIC methods applied in other contexts? I'm not really sure what we mean by UIC methods. I'm not familiar with any way that the UIC methodology takes into account the level of curvature. UIC methodologies tend to work on the basis of a given curvature band, whether it's over 250 meters curve radius, whether it's tighter than 150 meters curve radius, and doesn't differentiate really a great deal in terms of transitions or indeed calculate clearances per se. So I'm not really sure we can draw a parallel with the UIC methodologies. What I'm really looking at is the methodologies that we're using in the UK and an alternative of using the very simple method that we've got, which has got inaccuracies, and replacing it with something that gives us less. So I really don't know enough about UIC to be able to comment fully on that methodology. I'm sorry. I've got Vlad down. It says you smooth the survey dividement, the roughness, so to speak. What length of filter you use? Is it 1, 2, 3, or 5? Bogey's about 1.8 meter long. Surveys go about 5 meters. What filter do you choose? Depends on, say, speed or category. Well, that's a very interesting question. A great deal of work gone into that one, Vlad. In the end, the filter length that we've focused on as being the best compromise of getting the roughness removed but retaining the transition has actually been a 10-meter filter length. So that's the one that we've used most successfully in terms of the mainline railway network. But if you were going to be looking at a railway network that habitually had tighter curvatures, such as, for example, London Underground, Docklands or something like that, then I think you'd have to think very seriously about reducing that length. But equally so, it will be a lot easier to do that if you've got point spacings more frequently. So I think the issue would be that for the mainline railway network, assuming the data has been measured to about a 5-meter spacing, a 10-meter filter is probably the optimum than that. But look at if it was a tighter network using 1-meter spacing and maybe bringing a filter length down to something more appropriate with the levels of curvature that you've got. I hope that answers that question. Caris Day, I've got a question here. When capturing gauging data, different survey systems, sorry, it's moving up my screen, as different survey systems drive the curvature in different ways. The smoothing of data is already included with some systems to a very extent. how we manage this to avoid over-smoothing gauging data, i.e. creating a risk of removing genuine kinks in the geometry, which we need to include in the gauging calcs. Again, a very interesting question, Karis. And one of the things about the choice of filter lengths is actually looking at it to say what happens if we apply a filter to already filtered data, and what does that do to our calculations? The answer seems to be that with a 10-meter filter, if you apply it 1, 2, or 3 times even, that it actually doesn't do a great deal to the overall geometry. Whereas if you have a longer filter, and one of the things that was being talked about in the early days of this was using a 35-meter filter, which is the traditional one for, shall we say, separating geometry from roughness. If we applied a 35-meter filter to it, then applying it twice did actually start to shift the shape of a transition. So one of the key things again in this is making sure that we have a symmetric filter, i.e. run it in one direction. You get the same results if you run it in a different direction. But trying to build in some tolerance to make sure if data has got some smoothing put into it, then you wouldn't smooth it again. But I think one of the key things is that if you can actually use, as Stuart Corrie mentioned earlier, if you can use the actual design data, which is what we're trying to do, then what would be great would be to use that without any filtering at all. And I think from a measuring system point of view, what will be good is if the measuring systems could actually produce a curvature plot that was a reflection of what design geometry is. And if you like, if a standard could be for a curvature that could be used for the emulation of track design geometry and include it in the data that's submitted, I think that would avoid the need to do any post-processing filtering. And I think that again would be much better. Okay, I've got a question from Tim Kendall. Would this improve the possibility of getting double trains through cross-rail tunnels, excluding platforms, or have you seen this taken into account in the work you did for DFT 10 years ago? Very interesting question, Tim. The question of double deck trains comes up quite a lot. I think the answer is that probably it wouldn't make a great deal of difference depending on the nature of the double deck train, because a lot of the double deck trains that we see are articulated and generally quite small in terms of bogey centres relative to some of the long rolling stock we've got that's got long overhangs. For confidence, and I'll say this because I, as you know, I did the work on Crossrail before actually we got even into detailed design on it. One of the things we demonstrated was that using the methodologies that we use in the UK for gauging allows us to get double deck rolling stock of a traditional UIC GB profile or GB plus profile through the Crossrail tunnels, provided the electrification is kept well clear and that the platforms are considered in terms of the normal height of a UIC platform. So I think ultimately we do have the possibility, when we find that Crossrail is running at capacity, for us to introduce double deck rolling stock with fairly minimal changes to the infrastructure. But that I think it's a result of the gauging methodologies that we already use in the UK allowing us to do that, rather than using the UIC methodologies that actually allow a lot of additional space between the vehicle and the infrastructure. Okay, I've got I've got a yes, thank you, David, from Vlad. Thank you. Have we got any more questions coming in? I don't think we have.
There we are. Thanks. Thank you, David.
Pleasure.
Any more questions for David while we've got the opportunity?
Yes, I just typed the question, if you can look at it.
Sorry?
Yeah.
Oh, Vlad.
Yeah,
I just put a question in the chat as well.
If you could put your hands up, that would help me in David.
Sorry,
then.
Vlad.
Yeah.
I see you dropped another one. In fact, I can see now there's Tim Dixon and Vlad coming up. So I'm just looking at, did you work on swap bodies stroke piggyback, and does D-gauge support such vehicles? There is more of a yeah. The issue is frankly that we work on any vehicle, and there will be benefits in using these methodologies on swap bodies, piggyback, or whatever. In terms of does D-gauge support such vehicles? Yes, we do. The methodologies that we use are agnostic to vehicles, and indeed we're constantly refining the methodologies that we use to calculate the vehicle movements for some quite significant new innovations that are being brought into vehicles. So yeah, swap bodies and piggybacks, no problem at all. Tim Dixon, knowing how certain survey methods work, could you then backwards calculate a curvature diagram and then apply the smoothing and then feed this back into the survey, or does this need to be taken into account and carry out the survey on day one? It's a very interesting question, because if you think about it, what we've actually got here is a process of differentiation, integration. It's calculus that if we know the position of the track, then it's possible to calculate the curvature from that information. But if you go back to your elementary calculus, what you realize is that if you integrate back, then you're losing a coefficient of integration in it, and it means that you cannot actually start to work out where directions go. There's certainly ways where you can try and reconstruct a true curvature diagram, but it is actually quite inaccurate, and I wouldn't recommend doing it where you needed to know the actual position. Far better to measure positions, calculate curvatures, and then work back changes to position, than try and do anything other than approximate what something might do to a position from a curvature diagram. Again, this takes you back into the realms of how we calculate curvature in track maintenance machines, and reconstruction of track geometry from versines is actually quite difficult. And you may remember versine trolleys and things like that, which are very, very good at showing you what the versines are. But when you start to plot out the diagrams of curvature and indeed plotting out the direction of track, then it very quickly starts disappearing off in the wrong direction. So I think really what you need to do is to actually have you really do need to know from a design point of view the position of things, rather than trying to work backwards from versines and curvatures.
That's great, thanks.
There we are. Any further questions, anybody? I think we're there.
I think that's about it. I think
Yeah.
I think everyone's either completely confused by it all, or we've answered all the questions. But I hope it's given some people an idea that, you know, just because we've had methodologies that work for us in the past, it's not about living on our laurels. That the world is constantly in flux in terms of what we can do. And indeed, the quest for, shall we say, improving what we're doing, engaging, is something that has never stopped. They might not be visible to people, but the methodologies that are used are constantly improved. We look to try and all the time get to the point where the calculations that we produce mimic what we find in real life. Many people can remember the days of where people would say, well, we've done a gauging calculation, it says that something won't fit, but we know it fits, so we're going to carry on run it. And even more to the point where someone will say, well, you've shown me it doesn't fit, but I don't believe you, so I'm going to try it. There we are, I've tried it and it doesn't, I've proved it. Now, the issue is understanding all of these. And if we look a bit beyond this, then what we can say is that people have possibly heard of things like probabilistic gauging as being something that's about to, shall we say, be used. Probabilistic gauging is a technique that basically says the world of gauging is actually probabilistic anyway. Although we talk about clearances as being fixed values, 100mm clearance, 50mm values, what we're saying is statistically that is the most likely maximum clearance we're going to get, so we're going to go with it. But in actual fact, everything is statistical. And what we're trying to do all the way through is to get the technologies that we've developed on the computer to be able to mimic real life as accurate as possible, which allows us to make the best possible decisions going forward. And definitely going forward, we want to get to the situation where we're spending a lot less money trying to correct problems that we don't actually have in practice. These are things that are being done underneath. The trick from our point of view is to make sure that what we do is introduce things that don't turn the world upside down, that give you tangible benefits, but aren't improvements for the sake of improvements. You know, if we're going to gain 0.1 of a millimeter, is there any point in doing it? But if we're going to be able to gain 10, 20 millimeters in platforms where we've got tight problems and where we've got accessibility issues, these are certainly things to introduce. And just keep an eye on this space, because these things are happening all the time. And one of the things I'm really pleased about working in D-Gauge is that we're actually able to play with a lot of these things, experiment with them. And in fact, my last 2 days have been spent in Derby with my engineering team, working out a whole series of things that we think we can do that are going to improve gauging going forward over the next few years. And, you know, these are exciting things to look at. I'm really pleased to still be working this area. And those people I can see on here who've known me in the industry for the last 45 years will know why I haven't actually retired yet, because I find it so interesting.
David, it's fascinating when you think about some of the cost involved with major infrastructure alterations. Yeah. And for those of you who see my presidential address, I was in Newcastle with the section up there last week. We're in a cash constrained world, big time, in the railway industry. So whatever we can do to reduce the capital cost and the operational cost of the railway, obviously rail being a naturally low carbon transport method, we don't want it to be priced out of existence. So the work you're doing is vitally important. So thank you. I think we've got another question for you from Stuart. So if I just open the floor to Stuart.
Thank you. When we did our initial work on the 700 for Thameslink, we found a structure that had a foul clearance of minus 180 odd millimeters.
Yes.
For a 700. I don't think we ever actually checked it for Electrostars, but there were 10 of them passing every rush hour.
Yes.
And none of them hit it.
That's absolutely the point, Stuart. And you and I have both got experiences of certain situations where the calculations conspired to give us a huge amount of conservatism, and the methodologies I've talked about today are all about trying to reduce that. But I think one of the key things that we must remember is that when we do our gauging calculations, what we're doing is building into those calculations what might happen. So, what happens if the track moves by 20 millimeters, if the cross level changes by X amount? What happens if the suspension fails? What happens if the vehicle's at end of tolerance and things like that? And these things do add up. And the issue about looking at it probabilistically starts to give us a feel for the likelihood of this. And I think the concept we have to look at going forward in our gauging world is to say that there is a possibility that, for example, that class 700, if everything went wrong at one particular point, it could conceivably hit at that point quite severely. But the chances are it's not going to go wrong. And we need to know the risk of that going wrong. Not only the risk from the point of view of saying what's the statistical likelihood, but what is the consequence of it? And as people keep pointing out to me, if you have a small tap on a cast iron footbridge, the catastrophe that could result from that is very different from having a container hitting a brick arch. So, there's a lot of things about risk and consequence that we've got to bring into this thing. And as Nick pointed out in what he said, we are moving forward to an area where cost is constrained. We really going to have to work on it. And if we bring into that the context of we're now about to try and electrify the high-hanging fruit on our network from an electrification point of view, trying to find the space to get electrification systems through a lot of these legacy structures without knocking them down is a real challenge to our future. And I think that one of the key things here is we really have got to focus as part of our electrification effort. And I'm really pleased that PWI is now so engaged with the electrification side of things, because frankly, it's the same topic just applied to something that's got amps and volts going through it that we have and we've been dealing with in the permanent way context for many, many years. And really what we need to do is to look at what we're doing in terms of the gauging physically and say, this can help us a huge amount where we think we're going to have difficulty in getting electrification through. And maybe, it's not a case of going forward with things like discontinuous electrification. Maybe we look at it and say, we can actually get this through here using the proper methodologies that are not allowing us huge amounts of conservative space.
I lived through
question is, how do we
the
do
Great
that?
Western era, David, and as the maintenance director for the Western route.
Yeah.
And you know, if you look at the number of listed structures and the various stakeholders involved there, it was a really challenging project. Understatement, by the way. So anything that we can do to provide a more simplistic way of not having to either lower the track or demolish bridges, it's got to be worthwhile, as well as providing sensible maintenance tolerances as well. So yeah.
Absolutely, and I think one of the things that we found on Great Western, of course, is we learned a lot from that project, and what we learned on that project is being applied now in our future work. We learned about what clearances are. We've also learned, for example, about what loadings and things need to be put into things. I mean, I remember disagreements across boundaries whether you include ice load or not. And I think ice load is only included in the overhead design from Newbury westwards, for example, or if that was the original intention.
I think, sorry, I might cut across Stuart by accident. Sorry, Stuart, do you want to come back in?
How do you do that without adding 500 quid to every time that structure is gauging assessed?
Sorry, say again.
So you apply some probabilistic gauging technique that's perfectly fine. Let's just sweep it that way. Yeah. Someone's going to come back and reanalyze that structure again and go, and they're going to hit exactly the same problem.
Yeah.
How do you embed that information?
I think that
route-wide?
The processes associated with, for example, applying probabilistic are being worked out as we speak within Network Rail, because if a structure is, shall we say, deemed to be acceptable in terms of providing acceptable clearance by probabilistic methodologies, then that probabilistic methodology would have to be applied going forward. It couldn't be done by then saying, well, we're going to try and go back to the old ways of doing it, because we know that it just won't fit. We've got new techniques. It's a question of horses for courses. If we've got techniques that allow us to get some of these structures clear safely without having to rebuild them, then the cost of ongoing analysis at that point is unlikely to match the cost of completely removing a structure and replacing it. It's horses for courses, economic case. All we're doing is bringing new techniques to the party and hoping that the railway world itself will look at these new techniques and say, we've got something here that we can use realistically to actually give us a more cost-effective railway going forward.
Thank you, Stuart. Thank you, David. We're 23 minutes past 1. Oh, I see we've had something pop up at the bottom there. David.
we've got another one on the Wigan.
Jerry,
yeah. It's the same on the Wigan to Bolton electrification completely, and there are a lot of discussion around the NEGO, especially around arch overbridges. Yeah, absolutely. I mean, interestingly, one of the issues was there was, I think it was the Farnsworth Tunnel was recently went through a fairly expensive modification, i.e. a reboring, to get electrification through. I think there were two structures on that particular route, Farnsworth and Bolton. Was it Bolton Tunnel? I think something like that. Anyway, the issue was that Farnsworth there was an old canal tunnel that was repurposed and used for one of the lines, and it looked as though it was virtually impossible to actually do anything with it. The analysis that was done demonstrated that in actual fact you didn't even need to go for probabilistic, that you could actually get electrification through, but unfortunately the whole process is of design from the point of view of getting that scheme to happen. The safe option of filling the tunnel in with concrete, with a low density concrete reboring, it was chosen before the techniques associated with getting tight clearances were mature enough to do that. The techniques that were used, for example, on the intersection bridge at Cardiff, if they were applied to Farnsworth Tunnel now, actually you wouldn't be reboring that tunnel. So again, you look at it and say, we've moved on with what we've learned, what we've put in practice. And I absolutely agree. We should not be demolishing a lot of our arch over bridges just because they look tight. We need to be looking at them seriously and saying what will fit through here and how can we fit it through.
Yeah, absolutely. Sorry, it was more of a statement I was making really than a question. And I'm sure that our project managers will be getting in touch with you shortly, David. So.
Oh, I sincerely hope so, because I mean, we're totally embedded in the rail industry to make it cost effective and get gauging, one of the things that, you know, is we coined a phrase many years ago about looking at capacity of the network when capacity was the issue. And I think that was one of the things that turned gauging from being something where you had a guy sitting in the corner of the PWI office that would, you go to him and he'd come up with the expression "no chance" on most occasions. Getting it from the point of view of recognizing that the physical capacity of our network is more than we thought it was, if we analyze it properly, and that it is actually the key to the future of the railway by allowing us to get bigger loads across faster trains, tilting trains, etc. And I think we've now moved gauging from one of these sort of Cinderella arts that was at the back of the PWI drawing office into something that's mainstream and really a fundamental part of how we get our railway network to perform well for the future, particularly if we're starting to look at the railways as being the ultimate in low carbon economy for transport going forward. And modal transfer. Come on, let's get all these containers off the M6 and M62 onto the railway with nice, clean electric freight that's capable of crossing the Pennines just like that. I'd love to see that before I retire.
David, so thanks ever so much, and thanks to Jerry there. I mean, I guess, excuse the pun, but David, the gauging is right in the middle of everything that we do in the PWI, isn't it? OH&E, platforms, structures, track, the whole lot. So thank you ever so much for spending the time this lunchtime to talk to us all, to take the questions. Hugely appreciated. So thank you very much. A round of applause for me, and I'm sure for others that are still on mute. So thanks ever so much, David. Thank you.
Thank you. And of course, you know, we're more than happy to talk around the PWI sections about it in more detail. And now that we're back in this real world, it'd be lovely to actually catch up with people.
Absolutely.
Yeah. Thank you. Thanks for the opportunity.
That's no problem at all, and thank you. Lunch and Learn, it's here to stay. I checked in with the PWI yesterday. We've got a good series that goes right into the future. I think there'll be a couple of breaks during the summer holidays and things, but Lunch and Learn is here to stay, and I'm really proud of the PWI for putting this on. It's a really good learning opportunity for everybody, and to build your network of railway infrastructure engineers that will help you solve problems in the future. So well done to the PWI. Thank you to David. And on that note, I propose to close this Lunch and Learn, and thanks everyone for turning up. Thank you.
Thank you.
Cheers.